So anyways, okay, today we're talking about radical functions. Before I get to that concept, let me kind of walk you through the four things we have to cover in this unit. Okay, and they more or less fit the same sort of pattern we did in the previous unit. Only in the previous unit we just talked about linears, quadratics, cubics, quintics, quartics, and the shapes behind those. They were all polynomials. Now I need to teach you about sorts of graphs and functions, but that don't have the nice polynomial shape to them. So we're going to spend 2 days talking about radicals. Radicals are square roots. Then we're going to spend 2 days talking about rationals. Rationals are fractions. Only the difference is previously when I've had you guys do things where we divide fractions, they always did divide evenly. Now we're going to talk about what happens when they don't divide evenly. Okay, so that'll be my half of the unit. Then Miss McCarthy is going to talk about exponential graphs and logarithmic graphs. And so there's about 3 main things we have to do in each of these 4 sections. We have to talk about the details behind what makes these functions special on their own. Like what are some of the special unique properties of things that are square roots? What are some of the special unique properties of things that are fractions? Okay, we'll talk about that. Then we'll talk about the graphs themselves and what the graphs look like on your calculators, including properties like domain, range, x-intercepts, y-intercepts, asymptotes, holes in graphs when those come up. And then the last thing we have to do in each section is remind you how to do the algebra behind each of these topics, including how to solve an equation. Okay. So each of these 4 sections, if you even want to write down the main things we're going to cover, where's my intro slide for this? Here's my intro slide. The intro slide here just kind of talks about some of the various functions that we've learned about. If you want to add to this, we're going to do radicals. Come on. The headset doesn't look cool if I'm just sitting right at my desk. Defeats the purpose. Radicals, rationals, exponential. I'll just abbreviate to exponential, and logarithms. I'll just abbreviate that logs. Okay, so those are the 4 main sections, and in each of these sections, the main things I need you guys to be able to do, you need to be able to graph them, you need to be able to solve them, and the first thing is you should just know the generic properties. For example, the first thing we're going to talk about with radicals is the main property of a radical is that you can't square root a negative number. Does that make sense? Little things like that. Or when we talk about rationals, fractions, we'll talk about the terminology behind numerators and denominators and how you can't divide by 0 in the denominator. Those sort of little subtle details. Does that make sense? Okay, so that's kind of our roadmap for the next little while. So let's start with rationals or radicals. Should really choose different words because it's the exact same word with one letter change basically. Come on. Killing me. And when Curtis was in the room and I was testing this out, it was wonderful, right? It was working everywhere in the room, and all of a sudden now it stops working. Okay. Okay, so let's do some review on what radicals are. So I just want to talk about the properties of these things first. Most of this will be where we begin. It'll be a review of terminology. Okay. So do you guys remember all these symbols, or all these words? Index, radicand, and radical symbol. You guys know what I mean by that? What's the index of a square root? 2. We don't write the 2 in that corner there, but a square root puts a 2 here, right? Well, we normally focus on square roots, but we could do cubed roots. We could do 4th roots. We could do 5th roots. So I need you guys to be aware of what that means. I give up. I'm just going to hardwire this thing in. So much for sitting in the back of the classroom. Nah, it's fine. I'll just sit on the corner like I always do. Just hoping to try something different. Okay, do you guys know in your calculators where to find the buttons for square roots, cube roots, 4th roots, and above? Do you know where that is? Math. Here, I'll even show you on the screen here. For any students who decided to not come today and are sleeping right now and are watching the video later, just so you know where it is, I'm talking about you, Emily. See if you actually watch this video. Anyways, call her out on the video, right? A kid's gonna watch this video 2 years from now. Anyways, okay, here's where the cube root button is. And then if you need to do a fourth root, you need to press this one here. Except you have to put the type of root in before you press the button. So you'd have to go like 4, then do math x root. This is how you'd fourth root a number. So like the fourth root of 16 is 2. You guys all familiar with that? So far, so good? Awesome. Okay, moving on. Okay, one of the things we learned last year, the year before that, is how to work with mixed radicals and entire radicals. You can have a number in front as a coefficient, or you can have the radical be just an entire thing underneath the square root sign. Do you guys recall how to convert between these two things? Okay, quick review then. Okay, let's say I give you this root 18. I usually go down when I draw this, but I don't have any room below, so I'll just go up. I would say that 18 is equal to 2 times 9. Right? 18 is 2 times 9, right? Which of those two numbers is the more useful number here, though? The 9. Because 9 square roots, what is 9 square root to? 3. Hence the 3 that's outside the square root sign, right? Whereas the 2 right here, 2 doesn't square root, so therefore the 2 is stuck under the square root sign. That jog your memory? Cool. Okay, so let's do an example of them. I don't want to do them all. Let's just do a couple. If I gave you root 50, what you're looking for is 50 has to divide to give you two numbers, one of which can square root. So let's say you did 5 by 10. 50 is 5 by 10, but that's not purposeful. Right? Sometimes I say it's not wrong, it's just not helpful. So don't pick 5 by 10, pick 2 by 25. Right? Because then the 25 is the useful number. 25 turns into 5, and you're left with a 2 left over. Sound good? When you go the other direction, when you have to go from a mix to an entire, it's even easier. All you do is you take the 4 and you times it inside the square root, but you times it inside twice because it's a square root, right? So essentially what you need is like 7 times 4 times 4. Bring the 4 inside as though it was 16. So 4 times 4 is 16. Times that by 7. What'd you get? Perfect, 112. Thank you. Make sense? Let's just do one more. I'll pick one with a variable. If I take this one with a variable right here, 3n, I have to bring the 3n inside the square root twice, which means it's going to be 5 times 3 times 3, which will be 45. But you have to bring the n inside twice as well, which will give you n squared. You guys recall doing this? Like this was a big part of grade 10 and grade 11 math. So these are like those subtle nuances of like the properties of square roots I need you to know. So if I can flash way past through that section there, that's what I need you to know in part A. Know what an index is, what a radical is, how to convert between them, more or less that's the review. So now for part B, now I want to spend a lot of time talking about, well, what does a graph of a square root function look like? And I'd like to do this one by hand to start with. So let's just do a rough table of values. We'll just go x and y. Okay. Give me a number for x. 1's a great value to choose. I'm going to put it just slightly down, because maybe you'll figure out why I'm leaving a gap in a second. But what is the square root of 1? 1, yeah. So I can plot the point 1, 1 on my graph right about there. Give me another value. 0. That's what I left the gap for. Square root of 0 is 0. What number multiplies by itself to give 0? 0 times 0 gives 0. Now, some kids might want to pick 2 here. And 2's not wrong, but does 2 square root nicely? Okay, what's the next reasonable number I should pick? Yeah, 4 makes sense, because 4 square roots to 2. So as I kind of fill in my graph here, 4 gives 2. The next reasonable number you should probably pick is 9, because 9 square roots to 3. There, that's the rough shape of this graph. One more thought. What about negative numbers? Can't use a negative number when you're square rooting them, right? That's not a valid thing, right? Like if I try to plug in -1, you get an error. If I try to plug in -2, it gets an error. And so this is probably the first graph that I've really covered in detail where when I talk about properties, the domain of this graph, often we say x is an element of the reals. That's no longer true. If you guys recall my vending machine analogy, I would talk about how like the idea of an input is that you put in $1 and then it gives you back a chocolate bar, right? Well, up until now, every single x value is valid to be plugged in. You can plug in 5 or 7 or a million or 17/2 or pi. They all would be valid. But there are now some inputs that are now no longer valid. Anything negative doesn't work. So anyone want to take a stab at what the domain of this would be? Fantastic. Good job. Yep. X is greater than or equal to 0. So this is the first time that we have a restricted domain. Usually when you have a restricted domain, you also have a somewhat restricted range as well. This feels so silly having it's going to take a while to get used to. Okay. Want to take a stab at the range? Well, let's talk about this graph. I mean, this graph is going to go continuously up like this. Slowly but surely it will get higher, right? Like, for example, would this graph ever get as high as 10? What x value would get you back an output of 10? 100, right? Because 100 would square root to get you 10, right? Will the y value eventually be 100? Well, if x is 10,000, sure, right? Will the y value ever be a million? Sure, if the x value is whatever a million squared is, right? So this graph is continually getting higher. It's taking its sweet time, right? But hopefully you'd agree, this graph is going upwards. But are there any numbers down here in the negative side of the graph? No. So actually the range is y is also greater than 0. That's your basic square root graph. And I've probably got a photo somewhere in here of it. Yeah, here we go. This blue graph right here is a photo of what the absolute value, or not absolute value, what the square root of an x graph looks like. Okay. And actually, this is a good place to talk about this next slide here. It's actually half of a parabola. Do you see how right here is a parabola? In red, your good old x squared graph. Well, here is the blue graph, the square root graph we drew, only it's only half of a parabola. The other half of the parabola would have been down here. But why don't we have the other half of the parabola down there? Anyone know? No. Well, the square root of 4 is plus or minus 2. So it actually does somewhat make sense that you could have graphs down here. What's the title of our unit? Non-polynomial. If I continue this graph down here, if I were to have, like, say, this parabola, and I kind of turned it sideways as a sideways parabola, it's no longer a function. Does that make sense? So for it to be a function, you can't have both halves of it, because actually these guys are inverses of each other. Right? Remember how we flip the graph side over side, like over the line y equals x? If I were to take the graph of y equals x squared, if I were to make them inverses, it would give you x equals y squared. That's the inverse, flipping x and y. Well, then to get y by itself, you'd square root both sides, so you'd get y equals the square root of x. You know how, like, though, in the quadratic formula, you have, like, the plus and minus portion of it? Well, if you included both the positive, oh my goodness, if you included both the positive and the negative half, it's not a function. Does that make sense? So we only include the positive half. That make sense? Okay. Let me go back here, because I also want to cover cube roots. You're expected to be able to do cube roots as well. So I don't know if you guys have another color you want to work in. I have another color. I don't know about you guys. Let's do a second table of values for the cube root of x. And then we'll talk about its rough shape and properties. Okay, give me a number for x. 0. Thank you. Good job. 0. What happens when you cube root 0? Still 0, right? Because 0 times 0 times 0, 3 zeros, is still 0. So it still goes through the origin on our cube root graph. The next point that's good to use is 1, because 1 also does cube root. 1 cube roots to 1. Okay, so that gives us this point here again as well. I'm not going to use 4 though, because 4 doesn't cube root. 8 does though. 8 cube roots down to 2. So it puts this point over here, 8 and 2. And it actually causes it to look almost like the square root graph, only it's a little bit lower in terms of y values, which makes a lot of sense though, right? Because doesn't a cube root of a number give a smaller value than a square root of a number? Wouldn't a fourth root of a number give a smaller value than a cube or a squared? But here's where there's a subtle change though. I can actually use -1 and like -8 and stuff like that. Do you guys know what the cube root of -1 is? It's -1, yeah. Because -1 times by -1 would give you +1, but when you do it a third time, it's back to negative. And this guy's -2. So this graph actually has kind of a shape that looks like this. It's kind of got like a wave shape to it. So the difference between a square root graph and a cube root graph is square root graphs, you cannot have negative values. It's not plausible. And we also choose not to take the bottom half of the graph because then it wouldn't be a function. However, with a cube root graph, all bets are off. You actually can have everything you want again. The domain of this graph is x is element of the reals, and the range of this graph is y is an element of the reals. This graph will eventually get very tall. It might take a long time. Right? Like, when will this graph get to 10 in terms of y? When will the graph reach a y value of 10? When x is 1,000. Because 10 times 10 times 10 would be 1,000. So if x was 1,000 and you cube rooted it, you'd finally be up here at 10. Right? Like, it will grow. It's going to take its sweet time. Even more time than the square root graph. So, follow that? Okay, so I've now accomplished part B, more or less. I've shown you what these graphs look like. Okay? And I've talked about some of the major properties to begin with. The last thing we need to do now is talk about how to maneuver them around the graph. So here I've just got some more photos just illustrating what they look like. Here is the square root graph, but we're only taking the positive of the square root graph because the negative half of the square root graph would then make it not a function. Right? So we ignore the second half. But if you want to get that negative square root graph on there, just throw a little negative in front of it. What would a negative sign in front of a graph do? Well, doesn't a negative sign flip this thing head over heels? Doesn't this blue graph flipped head over heels give you the red one? Here's some more pictures. What's different about this square root graph? Is it in its traditional location? What would the equation of this be? You don't want to take a stab at it? Where would normally the square root graph start? At 0, 0, right? And it would go up like that, right? It's been shifted over. How far has it been shifted over? There's the equation. Right? We can now use the properties we've learned in the previous section to be able to just look at a graph, and we should be able to tell you what the equation is because it's been slid over 4 units, right? The -4 inside the square root function slides it 4 that way. I mean, you could graph it if you want to. I haven't used my calculator yet because I'm trying to avoid that. But let's try graphing one of these now. Y equals the square root of, and then in brackets, x minus 4. Look, there it is. It starts on a dime. Like, it literally just starts right there at a point. Everything on this side of it right here, everything on this side of it over here doesn't exist. Brooke and Jessica, when we talk about limits in calculus, the limit as x approaches 4 then doesn't exist. Because it does exist as you approach from the right-hand side, But as you approach from the left-hand side, there is literally nothing on the left-hand side, right? So therefore, right here, it's discontinuous. You know what I'm saying there? Sorry to the rest of you who aren't in my class there. Okay, so the exercise I want to do here then is I want to sketch a graph of the square root of x plus 2 and the graph of the square root of x plus 2, which your first thought may be, isn't that the same thing up there twice? But I actually wanted to do this to prove a point. I'd like for us to do the square root of x plus 2, and then I want us to do the square root of x plus 2. You catch the subtle difference there? In one of them, I want to square root the x, stop, then add 2. In the other one of them, I want to square root x plus 2. Okay. That subtle difference, changes it, right? This guy right here, really, what are you doing to your square root graph? You're moving it up to, yeah. So this one, just start here to there. Yeah, it should look roughly like that. That's this guy. And then if you have a different color, green, sure. Which way does that one go? Sure, left. Usually when I draw these, by the way, here's how I draw them real fast. I draw the initial starting point. I go over one and up one. And then I say good enough. That's roughly the shape. Okay. I mean, you can be more exact and actually pull out a table of values if you want, but I mean, for right now, I just need you guys to be able to visualize the rough shape of what this graph looks like. So far, so good? Cool. Okay, here's a slide just kind of reiterating what I talked about then. You could take a square root graph and you could manipulate it all over the place. You could throw an a value in front. Well, that would just make the graph taller. You could throw a b value right here. That would like squish the graph in or maybe pull it out. You could minus an h here or add a k here. That just slides the graph over or up. That's all. Right? So all of the same rules that we've learned in the past, well, they still apply. You just take your base level square root graph, which looks roughly like that, and you just move it all over the place. So let's try one. Without using a graphing calculator, let's try to get the rough idea of what a negative 5 root x minus 1 minus 2 would be. So first, I would just start by getting an idea of, well, what does a rough square root graph look like? It looks, I don't know, about like that, give or take. Like I literally plot the 0, 0 point, the 1, 1 point, and then I kind of just rough it from there. I mean, it should have gone through 4, 2. That's pretty close. It should have gone through 9 and 3. Close enough. Okay, so let's talk about our transformations. What does the negative do? Which way? Side by side, upside down. Okay, so it's upside down, and then the 5 makes it 5 times taller. So like to kind of work in between right now, I need a graph that's going to go upside down and be 5 times taller. Now, you know how I told you I only plot 2 points? Those 2 points are not going to be here and here anymore, though. Because if it's 5 times taller, this point is now way down here. That's all. So this is a much taller graph. Something like that. See what I meant? The 0, 0 doesn't change. The 1, 1 gets flipped over so that it's a negative 1, and then I stretch it way down here to negative 5. Like this point over here, when it becomes 5 times bigger, it's way down. Anyways, I have the rough shape of it, right? And then last little bit, I have to move it over 1 and down 2. So I can play a little trick here that you guys can't. I'm going to literally pick my graph up and move it, come on, over 1 and down 2. I can do that. You guys can't. You'll have to redraw it. However, the key point that I want to talk about is this sort of like initial starting point. I believe its official name is it's called a vertical tangent, which the two of you guys taking calculus, I might have put that in the notes in our calculus class. I believe that's the official name for this point where it just randomly just starts on a dime. I believe it's called a vertical tangent. I'll look into that. Anyways, that point though is at 1 and negative 2. And then, yeah, it's just a really tall upside down square root graph. If I want to now, I could then go to the graphing calculator. And then let's try typing it in. -5 square root of x minus 1, then -2. And if I go to my graph, hopefully it more or less looks like what I drew. Right? An upside down radical graph that's been stretched taller, which makes it just more negative, that's all. And then it's been slid over. Now, if you were to do a trace, you guys ever press the trace button before? Which is like if you press the side-to-side buttons, it tries to find where the points on the graph are. What some kids try to do is they try to figure out where that starting point is by like just tracing where the little X on their calculator is. That will not work. Okay. If you want to figure out where this graph starts, you have to figure it out by your knowledge of how transformations works. To the best of my knowledge, there is not really a calculator function that can find you where that little point just randomly starts there. There's a couple of things that occasionally work, but a catch-all that works in all cases, I haven't found one yet. Because if you try tracing it, it looks like this little dot right here is currently on like the end little point, right? But look at the values it gave me, 1.063 and -3.2. Well, those aren't actually the correct values for where we know it starts, right? Another option is you can go to your table and you can look for the last point that doesn't give you an error. And so the last point that doesn't give you an error was 1 and -2, which was the last point right here that works. Here's the only problem. What if I change my graph so that it's x minus 1.5? Right? Well, then if I make it x minus 1.5, that would have slid the graph over just slightly more. You know what I'm saying there? And if you looked at your table of values, I know the last point should have actually been at 1.5, but it actually put it at 2 and negative some other stuff, right? The reason being is that this was going up in increments of 1. It wouldn't catch an increment of 0.5, right? So if you want to figure out where this point is, the only really way of doing it for sure effectively is being able to look at your graph and saying, well, this -1 slides it over 1, this -2 slides it down 2. There's the logic. Sound good? Okay, here's a picture that I found on the internet, just kind of reminding you again for like the, I don't know, 6th time in these notes here how this would work. If you put a 2 in front of the root x, it makes it twice as tall. If you don't do anything to the root x, it's just normal. If you put a 0.2 in front of the root x, it would just make it shorter, that's all. Right? All of those transformations we learned can still be applied. You guys can kind of see why I'm taught the course in this order, hey? Because now that we've learned these transformations, they're not going away. We'll still keep using them. So that list of all the transformations on the back of your pink sheet of paper, I promise you, by the time we're done, all of this stuff, you won't need those written down anymore because you'll have them memorized because we use them for every single function. Okay, here's a slide just talking about the basic properties of these graphs, just like I've been doing on one of our earlier slides. Square root functions are always greater than 0 for domain and range. Until you move them around though, right? As soon as you move the function around, it changes the domain and range. If I can hop back to this one right here, what would the domain of this function be? Well, now x has to be greater than 1, right? Because I don't have any values over here where x is 0. And if I asked you for the range of this graph, y would have to be follow that? Right? Like there are no values up here. There are no values over here. So your domain and range is typically greater than 0 for both, right? Except if you move your graph around. If you move your graph around, that changes it as well. Right? So, if you're talking about a cube root graph, it's back to being everything because you can cube root. If they give you 4th roots, well, it's kind of similar to how we learned about even and odd functions and polynomials. Really, a 4th root is back to looking like a square root again, where you can't have negatives under 4th roots. Right? But you can have negative 5th roots. Can't for 6th, can for 7th. So I don't expect you guys to get 4th roots. As far as I understand, they really only want to do square and cubed, but you should be able to extrapolate. If I talk to you about a ninth root, you should know that ninth roots can be negative. I don't know why I'd ask you about a ninth root, but okay. Explain to me what's happening in these functions. What does the 3 in front of the root x do? Okay, right? If I put it in vocabulary, this would be a vertical, stretch, I guess, by a factor of 3. Or as Talia just said there, it makes the graph taller, right? So without using a graphing calculator, what would that do to the graph? Well, it would take my good old-fashioned graph that looks somewhat like this, and it would just make it taller, that's all. So far, so good. Okay, what about the second one? What happens when you put the 9 under the square root sign? Anyone want to take a guess? There you go. Yeah, you got it. Yep. So the 9 would take the graph and it would squish it in. So maybe I'd call it a horizontal. Let's call it a horizontal compression. But by what factor, though? What do we say it's compressed by a factor of 9? If I called it 1 over 9, let's say that it was expanded by 1 over 9 then. You know what I'm saying there? Well, compressing it horizontally by a factor of 9, watch this. If I were to take this random point right here and squish it in by a factor of 9, that would bring it into there. And if I took this point right here and I squished it in by a factor of 9, that would bring it into here. The point I want to make, these are the same graph. Because this is one of the first things I started with. 3 root x is the same thing as the root of 9x. Doesn't 9 actually square root? If 9 actually square roots, you can pull it in front as a 3. These two graphs are one and the same. I can actually accomplish the same thing through 3 different methods. I could make every point 3 times taller, and that would take me from the dotted line graph to the solid line graph. That's one option. But another option, which would get me to the same place, is I could squish all of these points in towards the y-axis. That would also work. There was a test question. You guys all finished your test now, right? Yes, you have. Okay. There was a test question on your unit final where it asked you about how many units you had to move that absolute value graph for the translation. If you guys know the one I'm talking about, right? The way it worked is that it was supposed to be over here, and then it was over here. One option was to flip it over the axis. The other option was to slide it over, and it was 8 units that you slide over. One of the things I need you guys to start picking up on is that it's actually possible to move a graph from one location to another location in multiple different ways. You could flip it, or you could slide it. Well, that same logic applies here. If you wanted to take the dotted line graph and make it the solid red line graph, option 1, make it taller, or option 2, squish it inwards. They'd actually both get you to the same spot. So here's an example then. I'm going to give you some points, and I'd like for you to try to figure out 2 possible functions that could fit this criteria. It's going to go through the point 0, 0, 1, 2, and then 4, 4. I'm just going to plot these points. 0, 0 would be right at the origin. Then 1 would be going through 2. And then 4 goes through 4. Wait, on your good old-fashioned just regular square root graph, what does 0 normally go through? 0 normally goes through 0. So that actually hasn't changed. What would 1 normally go through? Normally it would go through 1. So normally it would be at 1, 1. But now it's up at 1, 2. Now there's a couple of possibilities. It could have been slid up by 1 unit. But actually I can rule that out though. Because if it had been slid up by 1 unit, wouldn't this 0, 0 also have gotten slid up as well? So obviously it's not getting slid upwards. So in order to make this graph become taller, one of your options might be that you have 2 square root of x, right? Wouldn't that work? Where you'd make your graph twice as tall. It was supposed to go through 1, 1, but now we'll make it go through 1, 2 by making it twice as tall. What if you made the point 0, 0 twice as tall? Would it move? No, that's good, right? Okay. Well, let's check that with the third point, right? See how I'm giving you 3 points to check this? I better check with one more point. Normally 2, actually no, sorry. Normally 4 would go through 2, right? That's what normally 4 would go through, right? But now if 4 has gone through 4, yeah, that seems to check out that it's doubled twice as high. So this is one possible function that could fit the criteria. The reason I want to point this out to you is, like, let's say that you get an equation on the diploma and you think the answer is supposed to be 2 root x. And then you look down at the 4 responses and you think it's that, and you look down at A, B, C, and D, and you see this: 1/2 root x, 4 root x, root 4x, and root x. Which is the other one? Yeah, you guys see where I'm going with this? Why I'm trying to lead you to that? Is that this also would work. You could take that 2 and put it back inside there twice and make it a 4. You could consider this to be a stretch upwards of 2. Or the other way of looking at it is with this point right here. This point was at 4, 2. And I've now brought it in so that it's now at 1, 2. How far did I bring it in? Well, to bring it in from a 4 down to a 1, I brought it in 4 times as much, hence the reason why there's a 4 right there. Okay. So be aware that square root graphs have multiple ways of writing the same thing. Does that learning moment make sense to you guys, what I'm trying to impress on you there? Okay. Okay, the last thing I need to talk about, part 3 of like my 3-part things we have to do, is, recap, we talked about generic properties of square root graphs, right? You can't square root a negative. You know what an index is. You know what a radicand is. You know what the number in front is. You know mixed versus entire, right? You know all that terminology, right? Part 2, you now know what these graphs look like. Part 3, you should also be able to solve these, though. Okay. And really, I'm not going to spend a ton of time on this because this was actually grade 11 curriculum, but there's a very likely chance that they will still test you on it even though it's grade 11 curriculum. So let's do a quick recap. I always liked my analogy from Pirates of the Caribbean, where Johnny Depp, I'd always say, wait till the opportune moment, right? What is the thing that you're trying to do in a graph, in an equation with square roots? What's the key to solving it? How do you get rid of your square root sign? Square both sides, right? But we have to wait for the opportune moment, right? Don't just start squaring the first time you see it, because that might not be the best time to do that. All right, let's try this first example here. I've got a square root right here. I could get rid of the square root by squaring both sides, but maybe it's not quite the right time yet, because there's this leading coefficient of -3 out front. That -3 would be taking your graph and flipping it upside down and making it taller. Well, I could just divide both sides by -3, couldn't I? If I divided both sides by -3, you'd now have the root of 3x over 4, and it would equal -3. Now's an opportune moment, right? Now's a good time to square. If you square this side and you square this side, won't the square root go away now? Which will just leave you with 3x over 4. And then when you square the -3 squared, make sure you're really careful. -3 squared is 9. Not -9, right? Well, times up the 4, 3x equals 36. Divide by 3, x is 12. You guys remember doing this? This was last year's stuff, but it could come up. Okay, so let's look at this one here. I have a square root, right? The main focal point of solving something with a square root is you square both sides, but don't just go, let's just square both sides. Here, I'll square this, I'll square this, I'll square this. It gives me x minus 3 minus 4 equals x squared. Like, you've totally butchered that, right? Because that's not how this is going to work. Right? isolate your square root. Get your square root by itself. So hopefully you guys can follow. If I bring the minus 2 to the other side, it gives me x plus 2. All right. Now is the opportune moment, to quote a super awesome movie. They're making like a fifth one, aren't they? They're making like another one now? Yeah, I thought so.
Alex Garrett, can you please come to the office for checkout? Alex Garrett, please come to the office for checkout.
It's like 10 minutes until the bell goes. I think I've got x squared minus 3x plus 7 if I do my algebra right. What did I miss here? Oh, it should be plus 3x. Is that what you're saying? Yeah, x squared plus 3x plus 7. Okay. I'm not going to keep going on this one because I just made up some random numbers here, but how would you solve this? Factor first, if you can, and then secondly, if you can't factor, use the quadratic formula. But I feel like I can probably not take the time and do the quadratic formula if that's okay with you guys. You guys know how to do that, right? But either you will get answers from the quadratic formula, or there also is the possibility that there are actually no answers, right? The answers you do get from this, though, are going to be those like square rooted answers type things, right? Like 3 plus root 7 over 5. So anyways, you guys feel good from there? Okay, let's try the other ones. On this example right here, we're at the opportune moment already, right? I already have my square root sitting by itself, so let's square root both sides. Okay, now here's the most common mistake kids make. They make a that. All they do is they square the 3x and they square the 1. What have I missed, though? The 6x, which is really like, you have to remember that 3x plus 1 squared means you're writing it next to itself a second time. So you do go 3x times 3x and 1 times 1, but don't forget about those middle terms. That's the most likely mistake kids seem to make. So don't do this. Do minus 9x equals 9x squared plus 6x plus 1. Make it equal to 0. You'll get 9x squared plus 15x plus 1. And if it's okay with you guys at this point here, we're at that same spot where you'll either get some answers or you won't. This could be an unsolvable question. Right? There might not be any solution to it. I don't particularly like the looks of how it's going to factor. So try the quadratic formula, and if it gives you answers, it gives you answers. If not, then it doesn't. Sound good? Okay. Let's try this last one here. We're actually already at the opportune moment, right? The squared sign is already, let's square this one. Let's square this one. This will give you x squared plus 4x plus 4. Don't miss that. And then it'll give you, why don't I FOIL that out? 5x plus 10. Shoot everything back the other way. It'll give you x squared minus x minus 6 equals 0. This one I'll actually take the time to solve, just because I can do it pretty quickly. This one factors. What does it factor to? What'd you say? X plus 3, or x minus 3x plus 2. Okay, so it looks like you should get an answer of 3 and of minus 2 then. I should point out one more thing here. You should always double check your answers. Because the possibility exists that when you check your answers back into the original equation, they don't work for some reason. Do you guys recall what that's called? Good, it's called an extraneous solution. And I'd like to actually help you visualize why extraneous solutions occur now. I can actually do a better job of showing you why. Imagine that we tried solving this a different way. What if I tried solving it on my calculator and I typed in x plus 2, and then I typed in the root of 5 bracket x plus 2, and I just typed two equations in y1 and y2, and then I graphed it. This is the x plus 2 graph. And this one right here is my square root graph. Do you see how it crosses right there and right there? That explains the two solutions. But hypothetically, it's possible that I could get like a phantom solution. I like that kind of concept. Imagine that when I was drawing this right here, one of the lines looked like this. And then the other graph was just in a slightly different location. Let's say that it looked like this, but it stopped there. Do you see how it would give me one solution right here? But you might accidentally pick up a second solution. The accidental second solution would be as though the other half, like the negative side of the radical, was allowed. If it was allowed, do you see how it possibly could have given you a second solution? But the problem is that for it to be a function, we only consider the positive one. And so therefore, you end up having what looks like two solutions, but one of them actually has to be not counted. Does that help you visualize what we're describing there? It could occur that you have your graph that looks like this, and then when you have your linear line that goes through it, oh, that was poor. Let's try that again. When you have your linear line that goes through it, it clearly crosses twice, no extraneous solutions, right? And therefore, when you had your two answers were both valid, right? However, it could be possible, if I draw this one more time here, where you kind of have your graph that looks like this, and then you have your other graph that would have looked like this. And this is the only true answer. There is only one answer because the other one's extraneous. But what's ended up happening is you picked up another answer because you solved it as though this other half of the graph was allowed. But it's not, because otherwise it breaks the rules of it being a function. And the other answer that you solved for is like that phantom answer down here. I ever give you guys the analogy of the Vietnam War veteran who like loses his hand in an explosion, but he still thinks his other hand is there? Ever give you guys that analogy for like for extraneous roots? Okay, well maybe I should take it from the top then. Ideally, you should have maybe two solutions, right? However, unfortunately, the guy blew off his arm in Afghanistan. Right? Now, I mean, some of these veterans, you ever heard of this before, where like they still feel like they have a hand, right? But the hand got blown off, but their brain still registers that it's there, right? If I were to ask you to like make a line across both of these guys right here, normally you'd have two solutions, right? But what if one of them wasn't allowed? You might still think that it crosses here and that it should have crossed here, but well, this hand is no longer there due to an IED? Yeah, that's what they call it. I'm thinking IUD, but that's a different thing. Anyways, I got off topic. Do you guys get what I'm going for here now? Right? So sometimes extraneous solutions are like a phantom solution that it would have worked, but only if this bottom half here was allowed, but we've just went through a whole lesson talking about that it isn't. So there's actually the possibility that both of them are extraneous. You could have a graph that's supposed to look like this, and then you could have another graph that's supposed to work like this, and you get two answers. And both answers are extraneous, because you've picked up two kind of like phantom solutions where there's like one right here and one right here. Does that kind of help explain where extraneous comes from? You're picking up an answer that never should have been there in the first place because that half of the graph would not be a function. So, okay, I think I've made that point enough. Last one. This is the last one, right? Perfect. I have like just enough time. You are going to get a word problem on the diploma. I do not know what unit. It could be a polynomial one, it could be a non-polynomial one, it could be exponents, logarithms. The last time we did this, I had a silly question about a Rice Krispie square. You guys remember that one there? It was the dumbest question in the world, right? I only made it just to illustrate the point that you might get asked this in a context of a word problem. Okay? So, I mean, it doesn't change a whole lot. You just have to be able to know what this function looks like. So Justin's physics textbook states the speed of sound in dry air is related to temperature by this function. Here is our graph, right? They've given us a graph. Question 1, what's the domain and range? Well, what a lot of kids are tempted to do is they take this crazy, crazy function and they try typing it into their graphing calculator. They go y equals 331.3 root oops, that's not a root. Root 1 plus x over 273.15. They type that in their calculator, and then they go graph. And then they call me over and they say, Chris, what's wrong? Right. So what I need for you guys to be able to do, though, is look at the equation and tell me, well, how did this graph get moved around? For example, what's this 331.3 going to do to the graph? Stretch it way taller, right? Currently, our graph is set to go from 0 to 10. This is going to make it 300 times taller. So maybe we shouldn't go from 0 to 10. Maybe we should be going on our window size from 0 to, I mean, at least 300, if not more, right? Let's go to maybe like 3,000. Right, there's the first thing we should change. Just because we know intuitively the graph is much taller. Now, I wrote this in a bit of a different order. What if I were just to write the plus 1 behind it? Would that make more sense if I wrote the plus 1 behind it? Okay. Here's the problem, though. This still has to get factored. I know it looks a little bit different, but that same principle of having to get factored still applies. So we actually have to factor out a 1 over 273.15. You actually have to factor it out. Which sounds dumb because you're like, how's that going to work? But maybe if I just show you the answer, it'll make sense. If you factor out a fraction of 1 over 273.15, it'll leave you with t for the first term, which kind of makes sense because you just pulled the fraction off the bottom. And then to make this last term be 1, this term right here just better be 273.15. Because wouldn't 1 over 273.15 times by 273.15, wouldn't that just give you 1? Here, Andy. Yeah. Grab some. Okay, so let's talk a bit more about how this graph would work. What does this 1 over 273.15 do? What if the number was 5? 5 would squish the graph in. So if it's 1 over 273.15, it's going to pull the graph out a lot. So we have a graph that's now way taller, pulled way out further, and then some kids might think that this plus 1 right here means that it got slid over 1 unit. It didn't actually get slid over 1 unit, though. It got slid over 273.15 units. So what I'm going to do is I'm going to take my x value right here, and I'm going to make it go as low as negative 280. You guys all took chem with me, right? What's 273.15? What's the relevance behind that? That's absolute 0. Yeah, which makes sense that now we're all in the negatives. Oh, what did I do wrong here? Oh.
Please come to the office for important messages. Also, just a reminder to students and staff that the road in front of the school isn't one way. Therefore, you should be going around the back of the school to exit the parking lot.
Okay, now I finally got a bit of a graph once I maneuvered it. Most kids really struggle with getting a sense of where the graph happens to be, but now I have a graph that way over here, this is relating the speed of sound and the temperature. If the temperature is absolute 0, what's the speed of sound? 0. If you were in outer space and it was like 0 degrees Kelvin out there, sound wouldn't even move. There's not even a medium for it to move through. It doesn't even have that ability to, right? And as the temperature increases, right? Now these are all temperatures in the negatives, right? This is negative, right? This is negative 20, this is negative 40, this is negative 200. As the temperature increases, the speed of sound increases. Right? I'm running out of time. I won't be able to finish this question, but to answer the domain and range, the domain is going to be x is greater than or equal to negative 273.15. Which from a chemistry point of view makes sense because it has to be bigger than that value at least, right? And from my graph point of view makes sense because I slid that starting point of my graph way over here into that corner. Last thing, then we'll stop. Second last thing, then we'll stop. What's the range going to be? Y is greater than 0. Nice, yeah. Right? Because that's where this point just started right here. Which makes sense. You can't have negative speed of sound. Okay. Last one here. If I wanted you to calculate the speed of sound at 20 degrees Celsius, all you'd do is you'd go to your, say, table and figure out what happens when x is 20. Does that make sense? Okay. I think I'll leave that there. The point I want to make, though, is that they might give you something like this in the context of a word problem. So be prepared for that. I can't tell you what unit, but they will give you a couple of word problems here and there. So, okay, quick summary. 3 things you should have learned today then. 1, we reviewed properties of square roots, indexes, radicands, mixed radicals, entire radicals. Basically, we covered grade 10 square roots in 5 minutes. Second thing we spent most of our time on, now you know what the graph looks like and its properties. You cannot have negatives, basically. And then last thing, do you know how to solve them? Right. Wait for the opportune moment, square both sides, be aware of extraneous answers. Sound good? Cool. Thanks, guys. Have a good weekend.